Okay, we were looking at the function given by this graph, and we found, first of all, one way to express that was y equals minus 5 sine x, but the goal was to get a bunch of different ways. And what we do out of this is we discover a lot of different, seemingly different trig functions that are really the same. And those are going to be called identities, the fact that those are really the same. So people started figuring out things like, well, we could add any multiple of 2 pi. I think the different people had different letters. People had like a little q or a big Q, because Q's fun. It doesn't sound exactly like an integer. Something sort of more from the middle or a little bit before the middle of the alphabet sounds like an integer. So K or N are pretty common. So I'm going to say N, where N is any integer. And positive or negative, and we talked about how we don't need a plus or minus because if this could be negative. Okay. And so this gives the same graph. I could put it, if I could put in a 17 here, and it would give exactly the same graph. It wouldn't look at all different, because it doesn't matter when you shift exactly 1 or 2 or 3 or 5, 17 periods, doesn't matter. In terms of the unit circle, that's because we're going an extra 2 pi n. We're going an extra n revolutions around a unit circle. We're not getting to any kind of different place on the unit circle. And we're going to do a little more investigating about the unit circle interpretation of this. So, in other words, the minus 5 is just to make this example a little bit more kind of concrete. What we've got is an identity. And it's not a real new one. It just says it's periodic. But some of the ones are a little bit new for us. It says that sine of x equals sine of x plus 2 pi n. And this is not an equation you would solve for x. Say, oh, what's the special x that you solve for? This is true for all x. For all x. And all integers. And it's really important that I'll say real x and integers n. It's really important that n has to be an integer, so you really shift exactly 1 full period or 2 or 3, not 3.7 periods. But then it's true for all x. Okay. Well, what else was true? We had a nice summary from Riley, I believe. Sine x, let's see, this function, let's go back to the function. It's this minus 5 sine x function. It also was, one of the other examples, was plus 5 sine of x plus pi. And so if you shift it a half period, pi shifts this guy to be exactly here, and then it's totally wrong, except, wait a minute, if this peak is where the trough was, oh, I just have to flip it upside down. And that flipping upside down kills the minus. Okay. And so this says that the way people expressed it was a half period shift is equivalent to a flip upside down. And we'll see a unit circle interpretation of this very soon. The identity version of it is that sine of x plus pi, that's the half period shift, is equal to minus sine x. Okay. Then what about quarter period shifting? That was even more interesting. Another version of this same one was people realized that you could have minus 5 cosine, but then you just have to make sure the anchor point is over here, or no, actually for minus it would be over here. And so we want to take a cosine, a negative cosine which would have a trough here on the y-axis, and move it over by pi over 2, and move it to the right pi over 2. So that's a little tricky with the minuses and the pi over 2s and all that kind of stuff. So that's an interesting one, that will shift it. Okay. So what is the general identity there? It's that cosine of x shifted to the right a quarter period. Well, that's exactly how to get a sine function. Okay. Okay, and so this is, and let me just emphasize, these are all for all real numbers x. These are not what we call conditional equations. They are saying these are the same function. No matter what x you put in, you get the same thing. They have the same graph, basically, is one way to say it. Okay. And then there's another one. Oh, and of course, people then said, well, what about you could combine these guys? You could add pi and then add any even multiple of pi, and you're still going to get minus sine x. Or you can subtract pi over 2 and then add an even multiple of pi and get sine x. So for example, like if we want to combine them, we could say cosine of x minus pi over 2 plus 5 pi, so plus like 10 pi, 5 multiples of 2 pi. That plus 10 pi doesn't do anything. But the minus pi over 2, that shifts it to sine x. Okay, so we do that quarter period shift, which changes it to the other version, the other function, and then 5 full period shifts don't do anything. Okay, and what was the last one? The last one was that if I have, let's say, sine, we could do this as cosine. We could shift it the other way. This was one version of it, x plus pi over 2. Let's see, if I take a cosine function and I shift it to the left, I get an upside down sine function. You can check that on your own calculator if you're worried about it. Just plot these two and make sure you get the same answer. Okay, now one subtle issue, which we kind of glossed over at the end because it was kind of, we didn't have a lot of time, is that this was one version of it. Other people had a version that was cosine of x minus 3 pi over 2 equals minus sine x. Well, which one is the right version? Is it that you take the cosine graph? Let me just go ahead and graph cosine x real quick so I can point to it. Is it that you take the cosine graph, here's a big version, and you shift it to the right by pi over 2? That's going to take this to here. It's going to take this guy, it's going to take it over to here, and that indeed is going to give you sorry, to the left. That was the right one. That's shifting it to the right definitely gives a sine. Shifting to the left, that's what we're doing here. If you shift it to the left, this guy goes over here, this guy goes over here, and that's going to give you a downward crossing at the origin. That should be a minus sign. But wait, what about, some people were saying shift it 3/4 of the period to the right. Well, that's right as well. Here's 1, 2, 3/4 periods. If you shift this over, again, you're going to get a downward crossing. So these are both correct. And the reason they're both correct is back to the periodicity. Okay, it's the periodicity of sine and cosine. Let me go ahead and add the version in for cosine. The exact same statement here is true for cosine as well. There, you can get a sense there's a lot of facts that are unexpected necessarily, a lot of general facts that come in here. They're both correct because, for example, cosine of x plus pi over 2, one version of this, that's just the same as cosine of x minus 3 pi over 2, but then plus 2 pi. That just simplifies to plus pi over 2. And so there's lots of different ways to think about these things. Now, one thing that didn't happen to come up, and I'll just give a tease for it, is what about like putting in a minus x? We know what happens, and you should make sure you know what happens with cosine of just plain minus x and sine of minus x. We've talked about that in terms of symmetries of these functions. But what about something like cosine of pi over 2 minus x? Now the x is negated. What's going on with that? Or what about like sine of, let's say, 3 pi over 2 minus x? And I claim that combining sort of all the stuff in this video and some stuff we already know, we could figure this out. But we'll go ahead and investigate it a little bit more.